So if you remember, last time we introduced how to find the groups, the pi groups, that are dimensionless groups needed to perform, for example, experiment on a certain fluid problem. Now we will see how we can use these results, these experimental results and dimensionless numbers to extrapolate from the model, the experimental model, to the real prototype, which is the real case. Okay. So for example, let us say you have a real life jet. This is a prototype, and you want to conduct a similar experiments. Of course, you don't have to have exactly same size. You can have a much smaller size, but the condition will be to have all your dimensionless numbers governing the problem equal. Okay, this is what we call similarity. Now, in order to, we have several conditions to satisfy similarity. First, you should have geometrical similarity, you should have a flow similarity, and we'll see what do we mean by this. So we can notice here the similarity of behavior between the real jet and the lab jet, and the fluid dynamics are very similar in both cases. However, the scale, the size is very different. Okay, how to deal with this? So we say that if to be able to extrapolate results from a model to a prototype, we have three main conditions. We should have first geometrical similarity. When we talk about geometrical similarity, this means that sorry, the model and prototype are geometrically similar if and only if all body dimensions in all three coordinates have the same linear scale ratio. So as I told you before, let's say if for the airfoil, let's say the chord length is divided by 10, also the width should be divided by 10. And all body dimensions should be divided by 10. For angles, they should remain the same. Okay, all angles are preserved in geometrical similarity. All flow directions are preserved. The orientations of model and prototype with respect to the surrounding must be identical. Okay, so this is the first similarity condition. The second similarity condition is kinematic similarity. Kinematic similarity requires that the model and prototype have the same length scale ratio and the same time scale ratio. So already the same length scale ratio is satisfied in the geometric similarity. We also should satisfy the time scale ratio so that the velocity scale ratio will be also the same for both. Okay. The motions of two systems are kinematically similar if homologous particles lie at homologous points at homologous times. So this means that I should satisfy a certain constant ratio for length scale and the same time scale ratio also, so that the velocity scale ratio is the same. Now, how to if you want use this in numbers, this means that all all dimensionless numbers are equal. If you satisfy that all dimensionless numbers are equal, okay, we can be sure, uh, that, because look, and for example, for the geometrical similarity, you just have to ensure if you have a sphere, just the condition for similarity is to have a sphere, okay, of any different size, it doesn't matter. And if you have, let's say, the flow here is in horizontal direction, here also it should be horizontal. Or they can have different velocities. The condition to have similarity will be just that the time scale is the same, and velocity scale and length scale. And we can see this through, in general, for example, if you are doing steady experiments, we don't have the problem of time scale ratio because it will not be transient. So in steady cases, this condition will be always satisfied for time scale ratio. Okay. Now, finally, we have dynamic similarity. Dynamic similarity exists when the model and the prototype have the same length scale ratio, time scale ratio, and force scale ratio. So the final scale to satisfy to be the same scale ratio is the force scale ratio, and this is related to dynamic similarity. So again, geometric similarity is a first requirement. Without it, we cannot proceed. But then we should make sure also that kinematic and dynamic similarity exists simultaneously if the model and prototype force and pressure coefficients are identical. So, as I told you, to satisfy these conditions of kinematic and dynamic similarity, we should ensure that all our dimensionless groups governing the problem are the same. Okay, and for the geometrical similarity, it's very simple to verify. We should just consider that we have preservation of angles and we have the ratio of lengths is the same. So let us take some examples on this. So as we already mentioned before, if you have to perform, let's say, an experiment on a airfoil shape or a wing, you can build a model with much smaller dimensions. So here, for example, all dimensions are divided by 10 and angles are the same. So to save money, time, and effort, it is possible to learn about large scale, which is the prototype, flows by doing small scale model experiments in labs for a fraction of the cost and time. However, to correctly extrapolate model flow results to full scale, flows should you should for the experiment you conduct to be able to extrapolate its result, you should satisfy the following conditions: geometrical similarity, kinematic similarity, and dynamic similarity. In summary, this is what we talked about before. So for example here, dynamic similarity between the model and prototype require equal force ratios. So for example, we already have seen together that what are the main, in such problems, okay, when you study flow over an object, the main numbers, dimensionless numbers involved will be Reynolds number. And here you will be interested into drag and lift forces. So you should have the coefficient of lift identical, and also the drag coefficient should be the same for both. So in this case, because all of these are defined as force ratios, so in this way you can ensure that the force ratios are the same in the model and prototype. So this will allow you to ensure the dynamic similarity between the model and the prototype. Okay, now how we determine what are the dimensionless numbers that are important to consider? We should perform the analysis we did last time about how to get groups. Okay, so if you want groups and similarity will be studied in the same problem. So let us take an example. A long structural component of a bridge has an elliptical cross-section shown in the figure. It is known that when a steady wind, so here it's steady already, because it's steady, you don't have the problem of time scale. So of course you will satisfy, if length scale is satisfied, then kinematic similarity will be verified. It is known that when a steady wind blows past this type of bluff body, vortices might develop on the downwind side that are shed in a regular fashion at some definite frequency. Since these vortices can create harmful periodic forces acting on the structure, it is important to determine the shedding frequency. For the specific structure of interest, d is equal to 0.1 meters, h equals to 0.3 meters, and the representative wind velocity is 50 kilometers per hour. Standard air can be assumed. The shedding frequency is to be determined through the use of a small-scale model that is to be tested in a water tunnel. For the model, we take dm equal to 20 millimeters, and the water temperature is 20 degrees. The question is, determine the model dimension and the velocity at which the test should be performed if the shedding frequency for the model is found to be 49.9 Hertz, and what is the corresponding frequency for the prototype. Okay. This is a typical example that we can have. So first, what we should do, we should read again the given and put what are the main parameters affecting our problem. So first, as you can see here, the first, of course, the first parameter is the velocity of the flow coming over your elliptical cross section. Okay. You have the dimensions of your ellipse h and so parameters h and d. Now, as I told you before, whenever you have a flow, so already you have v h d. Whenever you have a flow velocity field, think about the density and viscosity, because they will affect the behavior of the flow. So we have rho mu, of course. They talked about vortices, and these vortices are characterized by a certain frequency, because they said here we will have these vortices can create harmful periodic forces, and it's important to determine this frequency. So we should add the frequency parameter omega, okay, and or f, you can call it as you like, f, let's say frequency f. Now what else? So mainly these are the main parameters. Let us check if there is anything else. Okay, so this seems that these are the main variables. Okay, now what do we know here? What are the things that we know about model and about prototype? So the prototype is always the real case. So this is the prototype. Okay, and this is the model. Before, if you want, we should just list what we know about the prototype and the model, and to determine what are our unknowns. So first, for the prototype, we know H. So for prototype, H is known, D is known. Air is, we have air blowing over it, so rho and mu can be calculated for air. And they told us also that we have the frequency is not given for the prototype, is given for the model. So f is unknown for our prototype. Now about velocity, they said that wind velocity is 50 kilometers per hour, so v is known. Okay. Now for our model, for the model, they want us to find the velocity at which the test is performed. So we don't know v of the model. Okay. H of the model also is unknown, because they said determine the model dimension. So we don't know h. D is known, it's 20 millimeters. We know that experiment is performed with water. So we have rho, we have mu. And also they gave us the frequency in hertz. So the frequency also is known. Okay. So we don't have, so in total, how many unknowns do we have? We have 3. And this is a hint for you. You know why? Because if you have 3 unknowns to find, then you can deduce that you have 3 groups that can be formed with these variables. And we'll verify this together by performing the analysis to determine what are the groups required, the dimensionless groups that can be formed for to understand the behavior of the flow in this case. Okay, and we'll extrapolate. We can extrapolate experimental results to the real case and we can determine what is the velocity that should be used in experiment based on this. So this is how they set the condition of experiment. They say, I know this about my prototype. I want the model to be representative, so I should have the same dimensionless numbers. So the first step will be to determine what are the dimensionless numbers involved, and then to set them equal, which will allow me to select the appropriate, if you want, velocity, okay, and that should be used in my experiment. And then, and also I can determine the appropriate value of h. And this will allow me, by performing experiment, I can measure, this frequency is measured experimentally. So once I measure the frequency experimentally, I can deduce the real frequency by using the similarity relations. Okay, so let us try together to do the first step and find the groups. So as we said, the first step will be to list all variables involved in the problem. So we determined already that these variables are the frequency, and this is mainly our interest, to determine this frequency. Okay, so this will be an output of our experiment. This frequency should be determined function of d, h, the velocity of the flow, and rho and mu. Okay, so now the first step will be to set the units of the dimensions of my variables. First, frequency or hertz, okay, in unit is 1/2. So it's scaling as t minus 1. So for omega, it's t minus 1. The diameter is a length, it's scaling as L. H also is a length, so also L. Velocity V is meter per second, so LT minus 1. The density is kilogram per meter cube, so it's ML minus 3. And the mu, the viscosity, we already determined the dimension before. It's m kilogram meter minus 1 second minus 1, so it's ml minus 1 t minus 1 in dimension. So now, after I list the dimensions of my variables, I can see that I have three, if you want, dimensions involved, which are m, l, and t. So now I can say that first, the number of variables n is equal to 1, 2, 3, 4, 5, 6, and j, which is the number of independent variables that cannot form a group, is smaller or equal to 3. So I will try to find 3 as we said last time. If I find 3 independent variable, it's fine. If not, I can reduce g and try 2. Okay, as I told you before already, you have 3 very simple variables. So here you can directly say, I am sure that d, v, and rho does not form a group. Why? Because rho is the only one containing m, and v is the only one containing t. So when I combine d, v, and rho, they cannot form a group. Okay, I cannot form a group with 2 of them or with 3 of them. So I can set the repeating variables as rho, v, and d. Okay, then how many groups I can form as expected in the in our analysis? The number of groups k is equal to n minus j equals to 6 minus 3 equals to 3. So I can form 3 groups in this problem. Okay, the first group will be by combining omega with my 3 independent variables. The second group will be by combining h with my independent variables, and the third one will be by combining mu with my independent variables. As I told you before, you have several ways to determine groups. You can use Buckingham theorem. Okay, in general, they should specify for you the method to use, and if not, you can use what you want. Okay, في groups هتعرفوهم دغري، يعني مثلا with mu and with rho v d will give you Reynolds, because this group يعني هيمرق معكم كتير. So you can directly say that the group with mu هو mu over rho v d. أو في كنت تحطوا rho v d over mu, because you can select the coefficient that you want for mu. If you set mu, coefficient of mu is -1, you get rho v d over mu. Okay. So this is the first group. The second group also is very simple. For d, has this h has the same length, same scale of d. So of course it will only be combined with d, and rho and v will not appear. So the second group is h over d over h, or h over d. It's similar. And finally we have for omega. Okay. Let us do, for example, here also you can buy, if you want, let us use the second method we learned last time, by elimination. Okay. Here, for example, here the problem is that we just have t. Okay. If we try to eliminate t, you have t minus 1, and t is only present in v. So you have v is l t minus 1. So if you want to eliminate t minus 1, you should divide by v. So you start by saying v over d to eliminate t will give me t minus 1 over l times t minus 1. Then t minus 1 will simplify, but another variable will appear, which is 1 over l. So now to get rid of, to cancel out l, I should multiply by d. So now so this is omega over v. Now I multiply by d. When I multiply the result by d, I get l over l, which is 1. So this is my group. The group of omega is omega times d over v. Okay. So the three groups involved in my problem are omega d over v, d over h, and rho v d over mu. You can tell me, what if I select other variables? No problem. You can select what you want. The condition is that the three variables are independent. You will form other groups, it's fine. But at the end, okay, at the end, when you apply similarity conditions, you will end up with exactly the same result. So whatever is your independent variables, the number of groups you can form is 3. And the final conclusion you will get will be similar. Okay. This is why you can select any 3 variables you want. And maybe they can ask you to give several possibilities of groups. Okay. Then you can say, I can select these variables, or I can select this one, etc. Okay. Let us continue. Once we determine what are our groups, now we can say that to be able to extrapolate results from experiment to real case, the 3 groups in the model should be equal to the groups in the prototype. So I can say that omega d over v model equal omega d over v prototype, d over h model equal d over h prototype, and Reynolds model equal Reynolds prototype. And this will give me the 3 unknowns in my problem. Because first, I can start first with the easiest group, which is d over h. So to maintain similarity between the model and prototype, I should satisfy first d model over h model equal d over h in real case. Keep in mind that I know 3 of these, so one of them is unknown, which is the model dimension. So I can determine what should be the model dimension in my experiment based on this relation, that hm is dm over d times h. I have dm, h, and d given, so I can get what is the value of h in the model. Okay. Now, and you can see that I was able to reduce dimensions. So in the real case, the value of h is 0.3 meters. Now I'm using just 60 millimeters. So instead of 300 millimeters, which is the real case value, I'm using 60. So I'm doing the experiment on a smaller scale. And also the same for d. For the model, I have 20 times 10 minus 3, whilst for the real case it's 0.1. So I am conducting my experiments on smaller dimensions. Okay. Now, The second similarity requirement will be that we'll have equal Reynolds number for model and prototype. And the unknown involved in this case is the velocity at which the experiment should be performed, because I want to determine what should be the value of the model. To do this, all I have to do is to take other terms to the other side, because I know all properties except velocity of the model. This will allow me to calculate the value of the model. Okay, and just pay attention for units. So for example, here the velocity in the real case is given in meter per hour. So don't forget to convert it to meter per second. All you have to do then is to divide by 3,600. And by replacing numerically, you can get the velocity in the real case. So as you can see, we also worked with smaller velocity in the experiment compared to the model. Compared, sorry, to the real case, to the prototype. Okay, and now finally, we still have to determine this is our final purpose. Our final purpose is to know what is the real value of frequency in the real case. So to calculate, to be able to find the real frequency, experimentally we measure omega in the model, and then we'll be able to deduce what is the real omega by saying that the third condition will be to have equal values for the third pi group, which is omega d over v for the real case equal omega model d model over v model. All variables are known except the real frequency. This will allow us to calculate the value of the real frequency. And of course, the unit of omega is like omega m, will be in hertz. Okay? Any question on this?
Doctor?
Yes.
It's very clear, but I lost connection in the beginning. Can you repeat what is J? N equals 6 in a number of
yes,
values.
exactly.
So J should
yes, Michelle, last time we talked about the number of independent variables. How you can determine what is the number of independent variables? J is this number, but from your analysis here, if you look at the dimension involved, number of dimension involved in the variables, it's LT and M, so it's 3, okay? But the number of independent variable is smaller or equal to 3. Why smaller or equal? Because sometimes, as we have seen in an example last time, some of the dimensions can combine together and be repeated in the same way. And for example, if you have, let's say, mt minus 1 times L, let's say, okay, one variable has this dimension, another variable has dimension of L, and a third variable has dimension of mt minus 1. It's true here that the dimensions involved are 3, because you have M, L, and T. But if you pay attention, M and T are always figuring out in the same manner, and they are not separate. You don't have them separate in one of the variables. So here you have mt minus 1, mt minus 1 in this third variable. So it's like it's a new dimension or equivalent dimension if you want. You can define a new dimension, which is mt minus 1. So then the number of dimensions involved will, if you want, will be smaller than 3 in this case. And the number of groups, the number of independent variables you can select is smaller than 3. It will be equal here to 2, for example. Okay? Why? Because if you have these two, if you try to combine 3, if you try to combine, let's say 3, you will not be able, because, for example, always mt minus 1 is configuring in the same way. So if you connect these 3, mt minus 1 L, L, and mt minus 1, you can form a group between them, because mt minus 1 can cancel, and you can, let's say, divide this variable. If you divide this variable by this variable times this one, okay, you will get a dimensionless group. And let's say this is variable A, this is variable B, and this is variable C. You can say that A over B times C has no dimension. So were you able to هلا of course بيكون في غير variables يعني مثلا let's say L empty minus 1 تنقول هن 6 اوكي وحده ثانيه عندها empty minus 1 L square واخر وحده الدايمنشن تبعها L4 مثلا اوكي يعني بتلاحظ انه مزبوط هن 6 variables وعندي 3 dimensions empty L بس empty عم يجوا مش in separate way عم يجوا always in the same form together empty minus 1 empty minus 1 empty minus 1 يعني كأنهم equivalent ل 1 dimension بدل 2 اوكي so when you want to try to form independent variables ما حتقدر تاخد any 3 variables يعني اذا بتجرب مثلا L مع L4 ما مع L ما بيزبط لانه ال بيروحوا بعض يعني if you can form groups between them اوكي اذا بتجرب A B C كمان ما بيزبطوا لانه if you do A over B C they cancel out so in this case you can only select two independent variables يعني مثلا اذا بتاخد B و C بيمشي انه هول ما فيهم يعملوا جروب لحالهم يعني L مع empty minus 1 ما بيقدروا يعملوا جروب لانه we cannot cancel L or we cannot cancel M and T. So in this case J بتكون مثلا 2 in the example I gave you now. Okay? And then you continue. So this is J. Okay?
Okay, thank you, doctor.
Well, any other question?
دكتور
Yeah?
إذا بدنا نعمل غير combinations يعني بهيدا الإكسرسايز بنستخدم غير independent variables وبنرجع نجمعهم.
Exactly. You can, for example, you can say another possible choice, okay, is to select مثلا H, V and mu, for example, okay. If you do this شو بيطلع أول جروب؟ D combined مع مين بتكون مع H يعني أول جروب بيكون D over H هيدا بعده exactly the same. Okay. Second group now I will combine rho with H, V and mu. شو الجروب